Okay, if you've got a car on a banked track, then the first thing you know is that gravity acts straight down. The next thing you know is that the normal force is perpendicular to the track. The track is banked either this way or this way. If it's banked this way, then the normal force is going to be like this. And if you want the track to be banked this way, which is fine, then the normal force would be angled the other way. I think that's obvious. Everybody understands that. If you have friction, then the frictional force is going to be parallel to the incline. Or is it? Okay. If it's parallel to the incline, well, yeah, if you're staying on the incline, the frictional force has to be parallel to the incline. So you got to draw a frictional force, and if the incline's like this, then you don't really know whether you're tending to slide down or slide up. If you're going too fast, you're going to slide up the incline. If you're going too slow, you're going to slide down the incline, right? So your frictional force could be here.
It is user error.
Could be here. Well, we're not going to deal with the frictional force. So if the incline is frictionless, if the coefficient of friction, static or kinetic, I'm not going to put a subscript on it, it means there is no friction. Whether it's static or kinetic, it's zero. So it doesn't really matter which it is. I think the book talks about a very icy track. Now you do have friction between tires and ice. Coefficient of friction is really, you know, sometimes even less than 10%, so you don't have a lot of friction. So you have this.
I do want to start some seeds, and I would like to do some asexual propagation too. So let's just use this time to grow plants.
Because the friction's absent.
Because again, at the end of the plant cell.
Well, now draw me another picture, which is these two forces. But then cross these forces out like with a wavy line and draw just the net force. I believe your text still uses a wavy line when it replaces the forces by something else. Just draw me a picture of two forces, because those are the only forces we have, and the net force. Okay, vectors have to be head to tail to get the net force. You kind of went head to head. I want to be careful about that. Right idea. Gosh, your normal force does have two components, right? see one. Oh, never mind, I see it up there. Okay. Okay. Well, this picture can be drawn this way, same as this one, except that now we're going to replace this vector with its two components. Component parallel to the gravitational force, component perpendicular to the gravitational force. So now I've crossed out the normal force. Now what can you tell me about these three forces? Well, don't say anything, but if you're in equilibrium in the vertical, meaning, of course, you're not sliding up or down, so and that's where you want to be if you're going around a curved bank track, because accelerating up or down leads to trouble. You go off the road one way or the other, right? You want to stay on the road. So you adjust your speed until you're stable on the road. And if you've driven on an icy road with a bank, you intuitively know how to do that. You're not doing the calculations. If you did, you'd probably wreck. But yeah, you do achieve this, because the alternative is you wreck your car. Hopefully not going fast enough to get hurt, but you don't want that to happen. Okay, so you're not sliding up or down. So you're in vertical equilibrium. No acceleration in the y direction. Thus, your picture becomes this. And this force and this force have to add up to 0. So I can cross this one out and cross this one out, and that's all I'm left with. The horizontal force giving you a horizontal acceleration. Now, if you're moving in a circle, do you want to have 0 acceleration? What happens if you're moving in a circle and your acceleration becomes 0? You go off in a straight line, which doesn't keep you on the road very well. Got to make sure you understand that. One of the demos where they had a ball going around a circle and then they opened the circle and the ball went off straight, right? Did not stay in the circle. Well, your velocity in a circle, again, if you looked at the derivation in the problems or the text, your velocity in a circle keeps changing, which means you have an acceleration. And that's the only way you stay on the circle. Now, we've talked about that before, but this is your centripetal force. It's toward the inside of the curve, because if your normal force is in this direction, that means the curve is banked like this. So the inside of the curve is in this direction. So there it is. There's your centripetal force. And now, your centripetal force magnet has magnitude of V squared over R. So you're gonna have to know R to do this calculation, because you don't get to choose the radius of the curve you're on. You do get to choose your velocity. So we have this. Now, if you know your angle, then you can calculate your normal force, and you can calculate this component of your normal force, so you calculate the centripetal force. So, given your angle, theta being the angle of the incline, and m the mass of the car, and, okay, when I wrote F centripetal as V squared over R, that's the centripetal acceleration. I neglected to put m in there for mass. Mass times centripetal acceleration gives centripetal force. The centripetal force that you need, or that you get on that incline, can be calculated just by analyzing the vectors, and very simple. And of course, leave that to you, because it looks like you did pretty well with the vector aspect of the homework. And having magnitude centripetal force tells you what velocity select. Now again, you're not programming an autonomous vehicle to stay on that circle. Okay. If you have an autonomous vehicle, the vehicle's not going to observe the radius of the circle. It could, but be the more difficult analysis, I believe. And it's not going to observe the angle. It's going to observe whether it's sliding this way or this way and adjust the speed accordingly, which is exactly the same thing you do. And a good autonomous vehicle will do it better than you will. Autonomous vehicle probably won't be able to reliably anticipate changes in the coefficient of friction. You can. You see a wet spot on the road, you know coefficient of friction is going to go up or down. Okay. You see a piece of dry pavement. Well, that's okay. Dry pavement is okay if you're in that circle, because then if you try to slide down, the frictional force of the dry pavement will keep you from sliding down. And if you're moving at a speed that keeps you okay on an icy circle, then it's not going to spin you off of a dry circle, right? And that gets into a whole different analysis that you might want to think about. Okay, well, there it is. Again, it's a little tough, a little tricky. But once you see it, it's really pretty simple. It's not easy to get there until you see it.